Every year, Americans pour about 370 million cubic yards of concrete, enough to pave a sidewalk from Earth to the moon and back. Twice. Every bridge you cross, every basement you park under, every hospital floor you've walked on. It all started the same way, with fire hot enough to melt steel inside a machine the size of a passenger jet, running continuously, 24 hours a day, for years at a time. Have you ever looked at a sidewalk and wondered what it actually is? Today we trace the entire journey, from raw limestone pulled out of a mountain to the moment a truck races a chemical clock to pour it beneath your feet. Stay until the end, because what you're about to see will change how you look at concrete forever. This is Directive 1. Here is what most people get wrong about concrete. It is not cement. Cement is one ingredient. Concrete is the final product. Cement is what makes everything else stick. Without that distinction, none of what follows makes sense. Cement is ancient. The Romans discovered that mixing volcanic ash with lime and seawater created a material that hardened underwater, stronger than almost anything they could quarry. The Pantheon, poured nearly 2,000 years ago, is still standing. But the cement we use today, Portland cement, patented in 1824 by an English bricklayer named Joseph Aston, is something different. Aston named it after limestone quarried on the Isle of Portland because the hardened material resembled it. That name stuck. What he couldn't have known was that his formula would eventually become the most widely manufactured material on Earth, with about 4.4 billion metric tons produced every single year. The process begins not at a plant, but at a quarry. Limestone is the foundation. Calcium carbonate, compressed marine shells, and coral accumulated over hundreds of millions of years. A single cement plant consumes roughly 1.3 tons of limestone for every ton of cement it produces. The stone is blasted loose with explosives, crushed on-site to fist-sized chunks, and loaded onto conveyors or trucks that feed it directly to the plant. Clay and shale come next. Iron, silicon, and aluminum oxides that will combine with the calcium in the kiln to form the compounds that give concrete its strength. Getting the proportions right is critical. Too much silica and the cement sets too slowly. Too much alumina and it sets too fast. Plants analyze raw material blends continuously, adjusting the mix before it ever sees heat. Here is where it gets dangerous. The rotary kiln is the heart of every cement plant, and one of the most extreme industrial environments on Earth. A typical kiln is about 15 to 20 feet in diameter and can stretch 300 feet long, roughly the length of a football field. It sits at a slight angle and rotates slowly, maybe 1 to 3 revolutions per minute, moving raw material through progressively hotter zones. The flame at the burning zone reaches 2,700 degrees Fahrenheit, hotter than the surface of some stars. Think of it as a slow-motion chemical furnace, tumbling rock through a fire so intense it triggers reactions that can't be reversed. The kiln never cools down. Shutting it down and restarting it stresses the brick lining that protects the steel shell. Most kilns run continuously for 3 to 5 years between scheduled maintenance shutdowns. If a forced shutdown happens, equipment failure, a power interruption, the brick contracts unevenly and cracks. Replacing the lining can take weeks and cost millions. The kiln doesn't stop because stopping it is almost as catastrophic as a failure. Inside that flame, something called calcination happens. At around 1,650 degrees Fahrenheit, the calcium carbonate in limestone breaks down. CO2 is driven off as gas, and what remains is calcium oxide, called quicklime. This is where roughly 60% of cement's carbon dioxide emissions come from. Not from burning fuel, from the limestone itself releasing carbon that was locked in rock for hundreds of millions of years. Higher up the temperature scale, at around 2,150 to 2,700 degrees Fahrenheit, the calcium oxide reacts with silicon, aluminum, and iron compounds to form 4 new minerals. And these 4 minerals are what cement actually is. The most important is called elite, or tricalcium silicate, the compound responsible for early strength. The others govern long-term strength, sulfate resistance, and setting time. What exits the kiln is a dark, nodular substance called clinker. It looks like gravel, roughly marble-sized, glowing orange when it first drops out. Clinker is concrete's DNA. Every chemical property the final structure will have is already encoded in those dark gray pebbles. The most surprising thing at this stage isn't the heat, it's what happens next. Clinker has to cool fast, from around 2,700 degrees down to below 200 degrees Fahrenheit in minutes, or its mineralogy changes and it loses strength. Industrial coolers, essentially massive metal grates with fans blasting air up through the clinker bed, handle this. The recovered heat gets cycled back into the kiln to cut fuel costs. The cooled clinker moves to grinding mills. A ball mill is an enormous rotating drum filled with steel balls, each weighing several pounds, grinding clinker to a powder finer than flour. Particle size matters enormously. A finer grind means more surface area, faster hydration, faster strength gain. A small percentage of gypsum, calcium sulfate, is added during grinding. Without it, cement would flash set in minutes, becoming unworkable the moment water touched it. Gypsum is what buys you time. Here's the question that hangs over everything we've covered. All of this chemistry, all of this precision, all of this heat, does any of it actually guarantee that the concrete poured under your feet will hold? The answer is more complicated than the industry usually admits, and we'll come back to that. Most people assume concrete trucks mix the material at the plant and deliver it ready to pour. That's not how it works. The finished cement powder is loaded into silos at the plant, sometimes stored for weeks, then shipped by rail or truck to what are called batch plants, automated mixing facilities that exist in or near every major city. A batch plant combines cement with three other ingredients: fine aggregate, which is sand, coarse aggregate, which is crushed stone or gravel, and water. The ratio of water to cement, the water-cement ratio, is one of the most critical numbers in the entire process. A low ratio, around 0.4, produces strong, durable concrete. A high ratio, above 0.6, makes the mix easier to pour, but creates internal voids as excess water evaporates, weakening the final product. Chemical admixtures, plasticizers, retarders, accelerators, give engineers more control over workability and set time without touching the water ratio. The concrete that leaves a batch plant has roughly 90 minutes to reach the job site and get placed before the chemical reaction inside it progresses too far. A concrete mixer truck isn't mixing in the traditional sense. It's keeping the concrete agitated so hydration stays uniform and the material doesn't stiffen unevenly. Drivers know exactly when their batch was loaded. On hot days in direct sun, that window closes faster. On cold days below about 40 degrees Fahrenheit, hydration slows almost to a stop, and concrete poured in freezing conditions may never achieve its design strength. One detail that stuck with me going through the industry's failure literature: a huge proportion of structural concrete problems trace back not to the plant, not to the mix design, but to what happened in the last 90 minutes. Water added at the job site to make pouring easier, cure blankets left off in a cold snap, pours made too fast, too thin, into forms that were never properly prepared. Here's the part that seems counterintuitive. Concrete gains strength for decades. It never truly stops curing. The strength engineers design for, compressive strength, measured in pounds per square inch, is typically specified at 28 days, when concrete has reached roughly 90% of its long-term strength. A standard residential mix might reach 3,000 to 4,000 psi. High-performance structural mixes can reach 10,000 psi or more, but that number only holds if the curing environment was right. Cure too fast in heat or wind, and the surface shrinks faster than the interior, introducing tension cracks. Cure too cold and the reaction stalls. This is the invisible gamble inside every structure you enter. What this tells us about the industry: concrete is the most widely used construction material in human history, and also one of the most misunderstood. It looks finished the moment it's poured. It isn't. The chemistry inside it is still running, still evolving, still vulnerable, sometimes for years. The most catastrophic concrete failures: bridge decks that spalled and exposed rebar, parking structures that shed chunks of ceiling, foundations that heaved and cracked, rarely happened because the mix design was wrong. They happen because of what happened after the truck left. We'll say what most won't. A significant share of the concrete placed in American infrastructure over the past 60 years was placed under conditions no engineer would approve on paper. Contractors pushed beyond cure windows. Inspections were insufficient. The cost of that is being paid right now, in the form of a national infrastructure deficit estimated at over $2.5 trillion. The concrete didn't fail. The system around it did. The environmental reality gets harder to ignore every year. Cement production accounts for roughly 8% of global CO2 emissions, more than aviation, more than shipping. The chemistry of calcination means a significant share of those emissions can't be eliminated simply by switching to cleaner energy. The carbon is in the limestone itself. The industry is testing alternatives, supplementary cementitious materials like fly ash and slag that replace a portion of Portland cement, geopolymer cements that use different chemistry entirely, carbon capture systems bolted onto kiln exhaust stacks. Some of these work. Most are still years from scale. Every ton of concrete poured today locks in a carbon cost that won't be paid off in the lifetime of the structure it supports. The next time you step onto a sidewalk or walk into a parking garage, remember, that slab crossed 2,000 degrees of fire, traveled hundreds of miles, and was poured against a 90-minute clock to get there. Almost nobody ever looks down. Everything around you hides a process this violent or a system this fragile. And most of it is still running right now beneath your feet, above your head, holding everything up. Which everyday material should we take apart next? And where are you watching from? Drop it in the comments.